Hello. Today we're going to prove this iconic formula. This tells us that the sum of all the numbers from 1 to n is equal to n times n plus 1 all over 2. So this lets you add, for example, all the numbers from 1 to 100 really quickly. Now there are a few ways to prove this problem, so I want to prove it in a couple different ways. The first way is we're going to do a proof by induction. Okay. And let me just review how do you do proofs by induction. So if you want to prove that a proposition P of n is true for all positive integers n, what do? You got to do two things. Part one, you got to prove that P of 1 is true. This is called a base case. And then part two is called the inductive step. You have to prove that whenever P of n is true, P of n plus 1 is also true. So prove that for all n in the set of positive integers, P of n implies P of n plus 1. If we can do this, that'll prove that it's true for all positive integers n. Okay, so let's prove it. So in our case, let P of n be the proposition that the sum from 1 to n of I is equal to n times n plus 1 over 2. Okay. So first, our base case, we got to prove that P of n is P of 1 is true. How do we do that? Well, P of 1 just says that if you plug in 1 on both sides, that it's true. So is this true if we plug in 1 on both sides? Yes, it is, because this guy here, all the sum of numbers from 1 to 1, that's just 1. And then this is 1 times 1 plus 1, which is 2, all over 2, which is 1. Okay. So we prove that P of 1 is true. P of 1 is indeed true. So now let's go to the inductive step. So we got how to prove that if P of n is true for some random positive integer, then P of n plus 1 is also true. So inductive step, assume that P of n is true for some fixed n, which is a positive integer. Okay, so what does that mean? So since we're assuming that it's true, that means that the sum of numbers from 1 to n is equal to this. Okay, so we're assuming this is true, and we want to prove that P of n plus 1 is true. In other words, we want to prove that the sum from 1 to n plus 1 I is equal to n plus 1 times n plus 1 plus 1 all over 2. Okay, because P of n is this formula. Okay, and here n's a dummy variable. So if we were P of n plus 1 is what the formula is if you change all the n's to n plus 1's. Okay. All right, so we want to prove that this is true. If we can do that, we're done. Okay, well, how do we prove this? Well, observe that if we take this sum, can we simplify this? Well, this is the same as the sum from 1 to n plus n plus 1. Okay. To add the first n plus 1 terms, you add the first n terms, and then after that, you just add n plus 1. Get the final term. Okay, but what's this the same as? Well, we know that we can replace this guy with this since this equation is true. We can change this to n times n plus 1 all over 2. Okay. And now, okay, question, does that simplify to this? Okay, well, since we showed that this is the same as this, to finish the proof, we just have to show that this guy is the same as this guy. So we want to show that this guy is equal to this guy. Okay, that's our goal. Okay, I think the easiest way to do that is just simplify both sides. Okay, so left side becomes n plus 1 times n plus 2 all over 2. And then if we FOIL that, we get n squared plus n plus 2n, so plus 3n in all, plus 2. So the numerator here becomes n squared plus 3n plus 2. Okay. And then the right side of the equation, if we simplify this, what we can do is make this all one fraction. We can rewrite this part where it says n plus 1, we can rewrite that as 2n plus 2 all over 2. Okay. And while we're at, why don't we distribute this n? So this becomes n squared plus n. And what do you know? This is true. Because if you add these fractions together, you just add the numerators, and you get n squared plus 3n plus 2. So this proves that p of n plus 1 is true. And there we go. We're done with our proof. Okay. Why is that? Because we proved the base case. We proved that p of 1 is true. And we prove that whenever p of n is true, p of n plus 1 must also be true. So therefore, by the principle of mathematical induction, we're done. It's true for all n. Is there a better way, though, that we can prove this theorem? A way that's more intuitive? Because our proof by induction, sure, it proves the formula, but it doesn't really show where it comes from. So I want to give an alternative proof, which in my opinion is slightly harder. However, it does more show the logic of what's really going on behind the scenes. Okay. And okay, we have two cases to consider. Case 1, n is even. Case 2, n is odd. So case 1, assume n is even. Okay. Well, if n is even, what does that mean? That means we can write n equals 2 times k for some positive integer k. And now, okay, if we want to find the sum from 1 to n of I, okay, well, n is just 2k, so we can rewrite it like this. And now by our properties of sigma notation, this is the same as the sum from 1 to k plus the sum, the same thing, but from k plus 1 to 2k. Okay. We're just splitting the sigma up into first k terms and then the rest of the terms. This is one of our basic properties of sigma notation. Okay. Now this k, 2k part, I'm going to rewrite this as k plus k. And why am I doing that? Well, we can take advantage of a property of sigma notation here. We're going to use this law that if you have the sum from, let's say, L plus 1 to L plus k of some sequence, this sum is the same as the sum that goes from 1 to k of A of L plus I. So this is a fundamental law of sigma notation. And why is it true? Well, what is this sum? We are adding the elements from A of L plus 1 to our last is A of L plus K. All right, now what about the sum on the right? Well, here the sum is only from 1 to k. However, the terms of the sequence are offset by L. So if I is 1, we get A of L plus 1. The L look a little clear, et cetera, et cetera, et cetera. And then our last term in the sum is A of L plus K. And hey, look, what do you know? These are the same sum. So, okay, I wrote L here, but if we let K, this K be L in this formula, we can rewrite this as something that looks more like this. So this becomes, instead of K plus K, we can rewrite this as the sum that goes from 1 to k of A of k plus I by this law here. Oops, except our sequence is the constant sequence. So it's not A of k plus I, it's just k plus I in our problem. All right. Now, eventually, where this is going is we're going to want to add these sequences together. However, we want to do it in a smart way that the I cancels out. That's my plan. And so what we can do here is we can rewrite this sum on the left. Let me show you how we can do that. We can rewrite it as the sum that goes from 1 to k of k plus 1 minus I for this sum. Okay, why can we do that? Well, this is just, we're adding the numbers from 1 to k, right? Well, this is also adding the numbers from 1 to k, but in the reverse order, because if I is 1, we get k. If I is 2, we get k minus 1, etc., until our last term, if I is k, we get k plus 1 minus 1, which is 1. Okay, so this is the same as this, which is just 1 plus dot 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 plus k. Okay. Now, even though I spoke in terms of dot dot dot, this ability to turn a sum like this into a sum like this is actually a theorem. Let me write the more general one in blue. We're using this property. The sum for I is 1 to k of a sequence AI. That's the same as the sum from I is 1 to k of A of k plus 1 minus I. Okay, this is the law we're using. All right. Okay, now why the heck did I do this? Well, it's because this sum has minus I, this sum has a plus I. If we add them together, they'll cancel out. Okay, and so we're going to use another law here. Let me write it in blue. We're going to use the law that if you have the sum that goes from 1 to k of AI plus the sum that goes from 1 to k of BI, this is the same as the sum that goes from 8 to k, 1 to k, sorry, of AI plus BI. Okay, this is just a fancy way of saying that if you add A1 plus dot 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 plus AK, and here you add B1 plus dot 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 plus BK, that's the same as doing A1 plus B1 plus A2 plus B2, etc., plus AK plus BK. Okay, this is another very basic law of sigma notation. Okay, so using this law, we can add these two sums together and obtain one sum. This is the sum I goes from 1 to k of, we add these together, we get k plus 1 minus 1 I plus k plus I. All right. And that simplifies to this inside becomes 2k plus 1. All right. And now we can use another property of sigma here. See, notice the I is not in here. And k is a constant, right? K is fixed. So when you have, let me write it again in blue. We can use another basic property of sigma that if you have the sum from 1 to k of just some number, let's call it c, this is equal to c times k. Okay, in fact, this is the definition of multiplication. When you multiply two integers, you're just adding the number by itself. You're adding it to itself a bunch of times, okay? So that means we can rewrite this as 2k plus 1 times k, all right? All right, now, what is k? Well, since n equals 2k, that means k equals n over 2. So we can rewrite this, you change all these k's to n over 2. So we can do this. Okay, and if we simplify this, this comes out to n times n plus 1 all over 2, which is the formula we wanted, okay? Okay, so that's what happens if n is even. Now, what about if n is odd? Case 2, assume n is odd. Well, if n is odd, that means we can write n as 2k minus 1 for some positive integer n. Okay. Normally for odd integers, I would do 2k plus 1. However, we want to include the case n equals 1 in here as well. Okay, and the only way, if it was 2k plus 1, then k would, and if n's 1, k would have to be 0. So, and 0 is not possible. Whoops. This needs to be a k, some positive integer k. Okay. So how can we solve this? Well, we want to find the sum that goes from 1 to n of I. Okay, this is really the sum. What is n? It's 2k minus 1. Okay, well, what we can do is this is going to be the same as the sum that goes from not just to 2k minus 1, but all the way to 2k minus two k. You see what we're doing here? Because this sum is the same as this sum, it's just this sum has one extra term at it has one extra term at the end, right? And now here's what we can do is, okay, since k is an integer, that means 2k is an even integer. And we proved earlier in case 1 that this formula holds for even integers. Okay, and in particular, we can use this deduction here. If you had the sum from 1 to 2k, that's the same as 2k plus 1 times k. Okay, the part that says that this is equal to this doesn't really depend on what n is. It only depends on k, and it doesn't even matter if k is even or odd. Okay, so that means we can rewrite this part as, what was it? This guy. I'll copy and paste that. 2k plus 1 times k for that sum, and then minus 2k. Now simplify this. We get 2k squared plus k minus 2k. But what is k in our case? Well, if we do some algebra here to solve for k, let me do it in red because I'm treating it as scratch work. We get k equals n plus 1 over 2. So that means we can rewrite this as 2 times n plus 1 over 2 squared plus n plus 1 over 2 minus, actually, this is kind of clumsy. I mean, I should probably, it'd be smarter to simplify this first. K minus 2k, that's minus k, right? Okay, so if we substitute this value for k in, we obtain this expression right here. Simplifying this, what do we get? Foil the numerator with itself. Denominator 2 times 2 is 4. Yeah, we can, this 2 and this 4 turns this term on the left to fraction over 2. And so now can subtract 2 fractions which have the same denominator. So we have n squared plus n all over 2, which is the same as what we were trying to prove. Okay, so we proved our formula is true for the odd case. And we proved it for the even case as well. And therefore, we have proven this theorem without needing to use mathematical induction. Although that's half true, because these fundamental, the basic theorems of sigma that I was telling you about earlier, you actually need induction to prove these. But that's because induction is such a fundamental property of the integers. In fact, you can't even define the natural numbers without using the principle of induction. Okay, but anyways, so that is an alternative proof of this formula for all positive integers n.